Fraud detection is critical in real-world systems like financial networks, review platforms, and telecommunications. But here's the hard truth: accuracy alone is not enough. In fraud detection, a false positive can ban a legitimate user, costing trust and revenue, while a false negative lets fraud slip through, costing money. You need to know when your model is guessing versus when it's confident. This brings us to uncertainty quantification. And for that, conformal prediction has emerged as the gold standard. It provides distribution-free coverage guarantees, giving you prediction sets that mathematically contain the true label with high probability. But there's a catch. When you apply standard graph-based conformal predictors to temporal fraud data, they fail. The prediction sets become overly large, destroying efficiency. Why? Because fraud data has two nasty properties that break standard calibration. First, fraud hides. Fraudulent interactions are often embedded in neighborhoods dominated by benign activity. This deceptive context dilutes the calibration signal. Standard methods treat the whole neighborhood as informative, which biases the calibration toward being overly conservative. Second, extreme class imbalance and temporal drift. Fraud is rare, maybe 1% of edges. This scarcity destabilizes class-conditional calibration. A few overconfident errors on the rare fraud class can spike the calibration threshold. Add in temporal drift, where fraud patterns evolve over time, and the exchangeability assumption crumbles, leading to even more conservative sets. To solve this, researchers from Emory University and the University of Illinois at Chicago propose ProtoCP, prototype-conditioned conformal prediction. ProtoCP is a framework designed specifically for edge-level fraud detection on temporal graphs. It improves calibration efficiency by focusing on fraud-relevant subgraph context and stabilizing scores under imbalance and drift. Let's break down the three core components. First, prototype-based fraud subgraph extraction. Standard calibration methods assume that locally similar edges share similar score distributions. In fraud graphs, this is false. ProtoCP learns a bank of prototypes in the edge embedding space. You have learnable fraud prototypes and normal prototypes. These prototypes act as anchors summarizing recurring behavioral patterns. During training, a margin-based loss ensures that fraud subgraphs are pulled toward fraud prototypes and pushed away from normal ones. This creates a structured prototype space. Now for calibration, we extract a subgraph for each edge. But we don't use all neighbors equally. We compute importance weights based on how well neighboring edges align with the relevant prototypes. This attention mechanism suppresses benign-dominated noise and highlights fraud-relevant context. The result is a fraud-informative subgraph that provides a much cleaner signal for calibration than the raw neighborhood. Second, prototype-conditioned relative nonconformity scoring. Once we have the context, we need a scoring function. Standard nonconformity scores rely on absolute prediction confidence. But under severe imbalance, these scores are unreliable. They can underestimate uncertainty for fraud cases or become too conservative. ProtoCP introduces a relative nonconformity score. For a center edge, we compare it against its weighted neighborhood. We encode three types of relative signals: prediction-level discrepancies, degree-based structural statistics, and motif counts like two-hop paths or triangles. These features capture local anomalies. If a center edge deviates significantly from its prototype-matched neighbors in terms of structure or prediction consistency, the score reflects that. The final nonconformity score combines the base prediction score with a learned function of these relative differences. This makes the scoring robust to the heavy-tailed probability distributions common in imbalanced fraud models. Third, temporal graph calibration. Temporal graphs introduce spatiotemporal dependencies. A single edge score can be noisy. ProtoCP stabilizes this with a lightweight, history-only diffusion step. For each edge, we smooth its nonconformity score over its temporal neighborhood using the prototype weights. We mix the edge's own score with its context, typically with a coefficient of 0.5. This diffusion smooths out local noise without leaking future information, respecting the temporal ordering. Finally, we perform Mondrian conformal prediction. This means we compute class-conditional thresholds separately for fraud and benign classes. This is essential. Without this, the majority class dominates the threshold. By calibrating class-wise, we ensure the fraud class gets proper coverage, even with scarce positive samples. Let's look at the results. ProtoCP was evaluated on 4 benchmarks: YelpCai, SFFSD, FTFD, and BankSim. The results are strong. ProtoCP consistently achieves the target coverage of 97 to 99% across all datasets. But the real win is efficiency. ProtoCP produces significantly tighter prediction sets than state-of-the-art baselines like NCPNet and CFGNN. On SFFSD, NCPNet yields a set size of 1.3, while ProtoCP gets 1.16. On BankSim, it's 1.14 versus 1.04. This efficiency gain comes directly from the prototype filtering. By removing benign noise from the calibration context, the thresholds become less conservative without sacrificing validity. Class-wise analysis reveals another advantage. Most baselines undercover the fraud class while overcovering the benign class. ProtoCP achieves target coverage for both classes, with fraud coverage reaching 95 to 98%. This confirms that the relative scoring and prototype conditioning effectively mitigate the instability caused by extreme imbalance. ProtoCP also handles temporal drift robustly. By analyzing the Kolmogorov-Smirnov distance between calibration and test score distributions over time windows, the authors show that ProtoCP maintains a smaller distribution shift than standard methods. The fraud class coverage remains stable across temporal windows, whereas baselines degrade. This proves that the prototype conditioning and diffusion successfully reduce the calibration test score distribution shift. Ablation studies confirm the contribution of each module. Removing the prototype module consistently enlarges prediction sets, showing that prototype-based extraction is key to reducing conservativeness. Removing the relative scoring module also degrades efficiency, proving that neighborhood relative discrepancies provide complementary signals beyond absolute confidence. ProtoCP introduces some computational overhead due to prototype matching and relative encoding, but the cost remains moderate. On SFFSD, preprocessing takes under 80 seconds and calibration runs efficiently per epoch. The trade-off is well worth it for the gains in uncertainty quantification. To summarize, ProtoCP demonstrates that to get reliable uncertainty in fraud detection, you can't just apply generic conformal prediction. You need to respect the graph structure, the class imbalance, and the temporal dynamics. By conditioning calibration on learned prototypes, using relative scoring to capture local anomalies, and stabilizing with temporal diffusion, ProtoCP achieves tight prediction sets with valid coverage guarantees. If you're working on graph uncertainty, fraud detection, or conformal prediction, this is a must-read. The code is available on GitHub, linked in the description. Thanks for watching. If you found this deep dive useful, hit subscribe to keep up with the latest in AI research. See you in the next one.